last video of the day, I uploaded this Python notebook for the solution of the model problem. Corresponds to the last video that I uploaded, called, I think, solution of the model problem. Loading the standard things. This is the strong form. This is the weak form. This is the residual for the element. Note that, as I mentioned in the video, the weight functions end up leading to the shape functions A. So that's why the residual or the element has as many entries as shape functions for that element. And then there's the Q times the gradient of, and instead of gradient of shape functions, you end up with just the basis function. Instead of the gradient of the weight function, you just end up with the gradient of the basis functions. And then here, source term times, and again, instead of the weighting functions, just the corresponding shape functions, where, A can take the value 1, 2, 3, 4 for the quadrilateral element. For the tangent, you need to linearize this in the direction of an increment of theta. So that means linearizing the flux, linearizing the source term. And then when you plug in, similar to the W's, when you plug in the discretization of the increment, you end up with just basis functions. So you end up with some derivatives, and then base function B. You still have the base function A that you had before, some derivatives, and then somehow you'll end up with shape function B and shape function A. And same here, some derivatives, and you end up with shape function A and shape function B. And so as you plug in the different combinations of A and B, 1, 2, 3, 4, you end up with this 4x4 matrix. This is the mesh. I also have the same mesh on the video. I'm just plotting the mesh, so this is what the mesh looks like. In this case, I have essential boundary conditions over the outer boundary, and I'm gonna initialize the inner nodes to be 0. So I need my shape functions for the quadrilateral element, and this is the key part. So how do you do that? How do you solve the problem? You start some initial guess. This is my initial guess for the nodes. Again, in the boundary, I have to apply the essential boundary condition. Everywhere else, it's just going to be zeros. And then the Newton loop is the outermost portion of the code. I start with like 0 iterations, residual equals 1, some maximum number of iterations, some tolerance. So while my residual is greater than some tolerance and my iterations are less than my maximum allowed iterations, I have to initialize the residual and the tangent to be zeros. I am doing the entire size, so the residual is size number of nodes by 1, and the tangent is number of nodes by number of nodes. So I'm going to fill out the entire residual and tangent. How do I fill this in? I need a loop over elements. So for each element, get the nodal coordinates of that element, get the theta values of that element. Then I need to integrate. So I need to do a loop over integration points. So I have the 2x2 Gauss quadrature rule. So here is my loop over the integration points. Because it's an integration, I need to initialize the element residual and the element tangent to zeros, because I'm going to keep adding to that in this loop. So okay, loop over integration points. I have my integration points xi and eta and the weight. I evaluate the shape functions. With the shape functions, I can evaluate my isoparametric map, so getting the corresponding x coordinate. I can also evaluate the Jacobian. So for that, I need the derivative of the shape functions with respect to the xi and eta coordinates. With that, I can evaluate the Jacobian, which is the derivative of x coordinates with respect to xi coordinates. Because I need to get gradients with respect to the x coordinates, I need the inverse transpose of that Jacobian. And then with that inverse transpose, I can get the gradients of the shape functions with respect to x. So initially I had calculated the gradient of the shape functions with respect to the coordinates xi, the parent domain coordinates. But I actually want derivatives of the shape functions with respect to x, but that is easily obtained. Just multiply the j minus transpose times this derivative of the shape functions times with respect to the xi variables, and that gives me the derivatives with respect to x. Once I have the derivatives with respect to x, I can evaluate this gradient of the theta with respect to x, which is what I want. The theta is simple. That's just shape function times nodal values. So that one is the same as the x. So the x is just shape functions times nodal values. The theta is also shape functions times nodal values. But I also need the gradient of theta with respect to x. And that one is shape function, nodal values times shape function with respect to x. So that's why I needed this step right here, because here I need shape functions with respect to x. That's it. So I also have the conductivity, which is a function of theta. And I also have the source term, which is a function of theta. And with that, I can integrate the residual. This should look exactly the same as the statement that I have up here for the residual. So residual is the integral of q times the gradient of the shape function a, right? And q is actually, I should have it over here, q is minus k times gradient theta. So if you go back here, so weight of the integration point, determinant of the Jacobian, and then this is what is inside of the integral. So k times the gradient of theta times the gradient of the shape function 0, and then minus the s times the shape function 0. And again here, k times the gradient of theta with respect to x times gradient of shape function 1, and then the source term times shape function 1, and etc. So this is basically just replacing the things that I have up there for the residual. For the linearization, I need to take a couple of derivatives, and then I need to evaluate this matrix. Again, integrate, so I have plus equal weight of the integration point, determinant of the Jacobian. And then here, what you have here should be exactly what I wrote here. So derivative of k with respect to theta times shape function b times gradient of theta with respect to x times gradient of the shape function a with respect to x. So if you look at this, derivative of k with respect to theta times shape function b times gradient, dot product of gradient of theta times gradient of shape function a. Then the second term is minus k times gradient of shape function b times gradient of shape function a. So that's the second term. Let's see. K times gradient of shape function b times gradient of shape function a. And then the last term is derivative of s times shape function b times shape function a. So the last term is derivative of s times shape function a times shape function b. I have minus signs basically everywhere, but that's just because it's like I multiply everything by a minus 1, so that should be fine. Also the residual. Yeah, that's it. So that creates the element residual, the element tangent. Then I need to assemble. This is the first option that I gave you, which is you assemble from the residual to the entire residual, so the one that is size number of nodes. And then what I said though is that not all of the entries of that residual are going to be 0. You can read the explanation there as well. So I need to obtain my R star I defined in the lecture notes and my K star. In this case, because my essential boundary conditions are in the first nodes, this is just partitioning, very, very simple. All right, so now I have my reduced residual, my smaller tangent. Finally, I can do the Newton step, right, which is get the increment and add that increment to my previous guess and continue. And then if you run this, it will start with some residual, and then it sort of got lost a little bit, but after the first 5 iterations, then it starts converging quadratically, and so it finally converged. So at the end of 9 iterations, it's pretty much 0. And yeah, and I just plot it so that you know how it looks like. The correct solution is x squared everywhere. So that's it. So hopefully this piece of code essentially solves a problem with the finite element method for some problem that could be nonlinear. And it doesn't have to be, I could change the mesh and this should still work because this code is fairly modular. So yeah, it should work for other meshes as well. All right, that's it. That's it for today.